to, where's the rock hammer? I'd like to sort of change topics a little bit and talk about volcanic hazards and uncertainty, and actually take this group of physicists and engineers and throw in a little statistics here. Yeah, unfortunately. So this is part of a large investigation that we have going. Some engineers, lots of geologists, some of the more recent work with Eliza Calder, who some of you know here, a group of statisticians from North Carolina, Spain, SAMSI's a statistics institute that the NSF supports. What are we talking about? Large mass flows, usually associated with volcanic kinds of activities, rock flows, avalanches, mud flows maybe, although we're not today going to talk a lot about the fluid phase effects. We need simulation tools. We need to ask a lot of what if. And in particular, if I happen to live in Mexico City, Volcán de Colima is a couple of kilometers away, and I want to know, am I going to make it? Am I safe living here? And where might I be more safe if I live on the northeast side of the city or the southeast side of the city? We've developed a code called Titan 2D. This is a large adaptive mesh, got all the sort of nice numerical tricks thrown into solving the Savage-Hutter equations, which are sort of a thin layer approximation of granular flow over terrain. We can incorporate natural terrain into our simulation. You tell us where you want to go, give us a digital elevation map of the area. We can actually figure things out, solve the governing PDEs over that terrain, and tell you where flow is likely to go, where flow will go, what the answer is for an assumption of basal friction, internal friction, initial data, a whole host of things that we don't know very well. What we'd like to do is to say, how can we look at the uncertain inputs that are present and sort of explore what isn't an answer, a simulation answer to these flow equations, but given uncertain inputs and given some assumptions about those inputs, maybe a probability distribution, give me a PDF solution, right? That's what we really want. So I can say something quantitative about the answer. Oop, wrong computer. So what will and won't be done? I'm not going to talk a whole lot today about some of the mathematical modeling. As I said, I'm not going to talk a lot about important extensions, erosion, two-phase effects. I'm going to keep it simple. I want to understand this question of uncertainty in order to make predictions. I want to ask questions about the friction angles involved, the basal friction, the internal friction of particle-particle motion, the volume of the mass flow, how much stuff is being ejected from this volcano or is collapsing from this dome. And I want to know something about what's the risk over time. I'd really like to know something like that. The ultimate aim is hazard maps. We're working with geologists at Buffalo and particularly in Latin America, and they want to make good hazard maps, right? And right now, what's the way they make hazard maps? They go out and they core historical flows from 10,000 and 20,000, 50,000 years ago, and they said, well, 50,000 years ago, a flow made it that far, so that's got to be a fairly dangerous area. And it was 100,000 years ago that flow made it that far, so that's not quite so dangerous. And they draw a line down the middle of the street, and they say, on the left-hand side of this line, you better evacuate, and on the right-hand side of the line, you're fine. That's the state of the art right now. We're trying to do something to make that more sensible. So as I said, we're going to start with the Savage-Hutter equations. You've got a granular flow down some sort of terrain. You think about depth averaging in the direction normal to the terrain. You do some terrible things to the physics, but hey, it works. It doesn't. It gives us reasonable kinds of numbers. It's a fairly complicated system of hyperbolic partial differential equations. You want to solve this over terrains that are, 10 kilometers in one direction, 5 kilometers in another direction. You'd like maybe 5 meter squared resolution. So it's a fairly reasonable simulation. For our Titan code, a reasonable kind of simulation might take a couple of hours on a single processor for one run. We want to do some reasonable exploration of parameter space given these angles and volumes and everything else we want to explore. We've got several tens of thousands of runs we'd like to do. It would take us about a year to do an honest-to-goodness Monte Carlo simulation with reasonable kinds of accuracy. It would take us a year of compute time on a single processor. So we'd like to do something a little bit better, thinking first about uncertainty propagation. This is the first trick First trick I'll talk to you about that uses some interesting functional analysis. We've just got something out in JGR to this effect. We've called this tool polynomial chaos quadrature. Don't ask me about the name. It's a long historical thing that it's got a cute acronym. Let me give you a 30-second overview. Imagine you've got some kind of evolution equation. du dt is some a of u, some nonlinear function, a nonlinear operator. It could be a partial differential operator. And you've got some unknown parameters a. Right? That could be a vector of unknowns. We'd like to think about u at time t is the initial data plus your favorite time stepping on that nonlinear operator, whatever it is. We'd like to take some moments of u. Well, what does that mean? That means take your favorite time stepping kind of thing here and think about integrating that over against some probability measure. Okay. Our basic tool here is to say, let's translate that integral over probabilities into numerical quadrature evaluated at Gauss quadrature points. What Gauss quadrature points? Gaussian quadrature says something about integrals against polynomials. Well, if I have some assumption about the vector of unknowns alpha, maybe they are normally distributed. For many good distributions, there are associated generating polynomials, right? Hermite polynomials are associated with the exponential e to the minus x squared. Laguerre polynomials are associated with what? Beta distributions. Jacobi's with gammas, I think that's right. Right, so there are associated probability distribution functions and generating functions. Well, let's use those polynomials, right, as the places, as the functions against which I'm going to worry about my Gaussian quadrature. I evaluate my unknown parameters at the Gaussian quadrature points associated with those generating polynomials. That's where I do my sampling using my favorite PDE or integral equation solver. And so I'm very intelligent about using my favorite solver, but at special points, namely Gauss quadrature points. It's intelligent sampling. It's not, it does, it's better than something like point estimates. It's better than something like purely random sampling. It's very intelligent sampling. We can do about an order of magnitude fewer calculations than truly Monte Carlo pure random sampling, right? So instead of having a year's worth of time, I'm down to about a month's worth of time, and I can actually sort of do that. I don't mind tying up my machine for that long. So it's Gaussian quadrature in the uncertain variables with our favorite PDE solver for the deterministic variables. That was key for us. Since we had a hyperbolic system, right, we've got to do special things to preserve the hyperbolic nature and to keep conservation and those kinds of things. And I didn't want to muck around with the solvers. So this was a useful thing for us. And I can make a hazard map using this. That is, I take our Titan code and I run it. In this case, I varied friction, the basal friction angle over some range. And I took initial volumes of a flow. This is a volcano in Mexico. And I looked at the historical data, sort of held my thumb up and said, okay, here's an approximation to what that historical data looks like. We made draws from that historical data using using these polynomial basis functions. And what I'm showing here is what is the probability that the maximum flow depth over time is greater than, say, 1 meter. We call that a catastrophe, right? If something at any point during the flow, if there's an event here, and I'm standing at any location around here, what if at any time during that event the flow got deeper than 1 meter? That's catastrophic. And now we've got a probability map for that hazard. Unfortunately, this is all conditioned on a flow event. That is, if something happened, if something went boom in the night at Pico, then here's the chances that I'm going to get basically killed by this event. We wanted to take this thing out, conditioned on this event. We'd like to do something about what's the probability over time, right? We want to ask that question. So in order to do that, I need to transport you for a moment down to the Caribbean, an island paradise. There's a lovely little island called Montserrat on the eastern Caribbean. You can't hear that quite well. This is Jimmy Buffett. I don't know where I'm going to go when the volcano blows. Right? So this is the capital of Montserrat, a town called Plymouth. This is advertising, basically. Come down and visit the island paradise in 1977. And it's lovely, except when something isn't right. This is the southern part. You're looking from the northeast, I guess, down the island. There's a volcano down here, the Soufri Hills volcano, that was dormant for 350 years, and in the mid-90s started erupting. And it's been erupting continuously since 96. Right? And it's been pretty bad. There's some nasty things happening there. Here's our little lovely capital city in 77, and there it is in 98. This has been wiped out by a pyroclastic flow that is somewhat deep. That's the church in the downtown. It's about a meter of stuff that's been deposited there. The island was, parts of the island were evacuated 3 different times until a very large event happened, overwhelming the town of Plymouth. An island population of about 10,000 initially is now a couple of hundred. 2/3 of the island is evacuated and you can't live there. Okay, this continues to erupt. One would like to know something about the hazard there. Montserrat's about 16K in length, about 10 kilometers in width. The Soufri Hills volcano is in here. I'd like to point out 3 things. The Tar River Valley goes off to the northeast. Plymouth, the capital, is here. And there's an airport called the Bramble Airport that used to be there. Focusing in a little bit, there's a lovely crater cone, a horseshoe, that's the remnants of a previous explosion that points everything small towards the Tar River. This is a lava dome volcano from right in about here. And what happens is the dome slowly grows with lava extrusion well inside this horseshoe crater for a while. And then it reaches some critical size where it's bigger than the crater walls and starts to go over the crater. So everything small gets shot down the Tar River. Everything that gets large enough to overcome the crater walls then can go off in several different directions, threatening Plymouth and areas up to the northeast. Our simulations, just to give you a clue of what's going on, this is a moderate size, 50 million cubic meters of material. So for those who do natural hazards, that's not a whole lot, that's not a large flow, but for all of us who grew up doing little hoppers that are this big, that's a lot of material. Soufri Hill sitting here, this lighter blue flow is going down the Tar River, and this Tar River Valley from the volcano head down to the ocean is about 3 kilometers, 60 seconds. Do the arithmetic, that's about 50 meters a second. These things move quickly. You don't want to have to rely on running or getting to your car, starting it up, and trying to.
That's not very fast.
That's not very fast compared to what some of these things do. That's right. So as I said, we'd like to ask the question of risk over time. So this second trick that I'm going to show you, our parameter space is, again, flow volume. That's really important for us. And this time we're going to look at the angle of initiation. Are things set off more in that direction or in that direction or in that direction? We're going to define our catastrophic curve. If the max height at any time is greater than 1 meter, we're going to define that as catastrophe. We'd like to define a curve. Zeta is this angle of initiation, right? Are the initial flows going in one of any direction? And then psi is some function of that angle. What is the critical volume so that a flow in that direction gets over to where Andy is sitting, and it's deeper than 1 meter at any point during that flow, right? So we start off by 256 simulations of our code in volume initiation angle space, and our critical curve lies someplace in here, and so we'd like to do a little bit of adaptive sampling. And so the green and red points, we're trying to focus in, doing extra simulation runs, focusing in on that critical curve to try to define it well, using some tricks of Bayesian statistics in order to be able to do 256 plus maybe a couple of dozen other runs instead of 40 or 50,000 runs, so that we can get our catastrophic curve, and that's, well, a bunch of things have overlapped here in the sort of purplish color. That's our critical curve with statistical intervals, plus or minus 2 standard deviations, right? We have quantitative measures here. We have confidence intervals, credible intervals for those in the Bayesian world, right? We've actually got quantitative information. There's our critical line, but I know that plus or minus 2 standard deviations gives me something else coming in here. And I can make quantitative predictions of how good that answer, that single curve, really is. Now at Montserrat, this is a lovely natural laboratory. As I said, the volcano's been going for about, sit down, Jim, for about 12 years. We've had several thousands of flow events happen. Here is a log scale of the volume and the frequency with which that a flow of that volume has happened. A lot of this stuff is just binning. Flow goes so far, they say, that's got to be about 10 to the 4th cubic meters of material. Oh, that one's about 5 times 10 to the 4th. That one's about 10 to the 6th. And once they get above about 10 to the 6th, they really start measuring things out. And so this ought to give pause to everyone and say, well, gee, there's something going on here. We can construct a Pareto distribution from that Montserrat data. Basically, we have a nice scaling that allows us to compute what's the probability that there'll be at least one flow greater than some V volume over T years, given parameters alpha and lambda, which have to do with that log linear distribution. Then I can compute a posterior distribution that says, okay, what's the probability that there's going to be a flow greater than our catastrophic curve value over T years? I can do all this statistics, and lo and behold, I can get an answer that says if I'm sitting in the center of Plymouth, the center of the capital, then this blue curve tells me what's my accumulated probability that I'm going to get run over by a large pyroclastic or avalanche flow over the next 10, 20, 30, 50 years. Or what's the chances over at the airport, the Bramble Airport? I can actually come up with these numbers right now with some degree of confidence, because I have statistical confidence intervals associated with these things.
You said you must move.
Yeah, that's one good thing. So what's in progress? Well, so we did one trick with these PCQ kinds of things, basal friction angle, and we know that in real volcanic flows, friction angles don't mean so much. Volume is important, and the effective friction is a function of volume. And so we need to incorporate that somehow. We're trying to work that out right now. We want to get a full hazard map, so we have to integrate in a couple of extra tricks along the way. It's just going to be a larger calculation. The digital elevation maps we use, they contain errors. It's tough to characterize those errors, but we want to figure out how, we're trying to figure out how to do that. And Montserrat is special, as I said. It's this thing that's been flowing, erupting constantly for a dozen years. There are other volcanoes we'd like to see where there's a little bit of eruption, or there may only be eruptions over geologic history. We've got 2 or 3 or 4 events. We'd like to know, how do we take that as field data plus a bunch of simulations and change that into actual honest-to-goodness probability maps, hazard maps, so that we can avoid stuff like that, which happens at Montserrat on a regular basis. So, thank you very much.
Any questions? Your critical curve had a nice maximum. The uncertainty were peaked in strange ways and strange direction. Why is it so?
Because of the terrain. As you're going down, there are channels going off in different directions. So you may have, at Plymouth, there's one principal channel that sort of heads in your direction. But there are flows that could come from other ways, right down, start off in different channels, but then come back and overrun the island of Plymouth. So what you're seeing in those likelihood intervals is an effect of all the local terrain affecting your probability, say in Plymouth. Yes?
Okay. You probably said it, but I missed the point. Which distribution probability you assume for the angle or the flow or this?
So when we did the chaos, polynomial chaos kinds of things, what we assumed uniform distribution of basal friction angle, and the volume data that we used was based on historical record, and we fit a beta distribution to that, basically. Within a half a dozen or so different reasonably well-known probability distributions, you have these associated generating functions, and so you can use the PCQ approximation to do that.
But if you assume a very different distribution, you get very different results?
What really is critical is how rapidly you get convergence. In principle, you've got orthogonal polynomials that can serve as a basis set. Everything ought to be okay. It's just how many terms do you have to take before you can stop. If you take the generating functions that are associated with your assumed initial distribution, you get rather rapid convergence. If you take something that's not associated with that distribution function, the convergence is much slower.
Okay, let's thank Prof.